Welcome to Lecture 25, Part B. During this lecture, we'll actually be looking at ways of practically using the eigenfunction we've shown to exist and to have a certain number of zeros to expand functions on them, or to expand any function on them. And this becomes extremely useful when we start solving especially separation of variable problems in the PDEs, where we actually, in these separable coordinates, we get functions that we want to specify certain boundary conditions, and then it becomes very, very natural to expand those functions on the Sturm basis. And in fact, the eigenvalues of the Sturm eigenfunctions then become associated with the frequencies that are possible in finding the solution. Okay, so I just want to do the first preparatory theorems during the second part, and show you how we actually go about computing the expansions. And then during the next lecture, I'll look at the specific example, or return to the example of the elliptic equation or elliptic membrane, and solve the wave equation there. Okay, so Sturm basis expansions. It basically says let's have our Sturm operator with all the nice properties that we've been using up to date. And we're going to solve the eigenvalue problem with the specific boundary conditions that we specified. And what I introduced, or sort of started showing in lecture 23C, is once we know we have these properties that are derived in part A, we can then have the eigenfunctions and that have an associated eigenvalue, and they form an orthogonal basis. Okay, and if you remember, we worked out a number of lemmas in lecture 23, just associated with the operator, and then associated with the operator and the boundary conditions, and then results associated if you actually solve the Sturm problem itself. Okay, and they're pretty straightforward to prove, and here we're simply going to apply them. Okay, so the eigenfunctions associated with lambda n form the orthogonal basis, and by orthogonal we basically mean that if we take the inner product of two eigenfunctions, which is thus defined as the integral from 0 to a yn of x, ym of x, w of x dx, that's equals to the delta function mn. Okay, and if ever this thing becomes confusing, we've actually used this type of thing when we worked out the Green's functions. And there are basis functions which are sine and cosine. So we're working out the Green's functions on a box, and there are basis functions which are sine and cosine. And we actually computed these integrals where the weighting function was 1. Okay, so in lecture 23, lemma 3, we basically showed that this condition holds, that you could basically show that the lambda m, the eigenvalue of 1 of m minus the eigenvalue of n, multiplying the inner product of two basis functions is equals to 0. So this thing results in either lambda m is equals to lambda n, right, in which we have to do more work, or lambda, the inner product of lambda n is with lambda m is 0. Okay, so the second part, if n is not equals to m, we basically have the delta function equals to 0, and that's proved here. Okay, so what we're going to do now is, in the case where n is equals to m, we just want to prove that the delta function is equals to 1. And the way we do that is actually to define our eigenfunctions to be normalized correctly. So remember, when we worked out in the part A of this lecture, we actually worked out that we proved that we could always find theta of x lambda n, that solved the pre-Fourier equations. And once we were given that, we could then go to the second pre-Fourier equation, which is basically d dx for ln of r of x is equals to its right-hand side. Okay, so I've just put down the integral version now. Okay, and theta is a known function of x and lambda n over here. Okay, so you could just integrate it, and you have that ln of nx over r0, and there's no way of fixing this r0 from the initial conditions. Okay, it's just equals to the integral from a to x of this thing, which is known. Okay, so compute this integral, not always easily. Then you have the ln of r. Okay, take the exponent and you have r explicitly multiplied with a function in front. Okay, and what we're going to do now is simply choose the function in front so that it is equals to, so that the inner function of, or the inner product of y1 and y, sort of yn with itself is equals to 1. Okay, so I'm just writing that out. R0 is not fixed by the boundary conditions. So we can compute our yn of x, and it's just Rn of x, sine theta of x lambda n. And then we fix the scale. So we basically fix R0 so that we have that yn comma yn, which is just defined by this integral. So basically yn squared, which we now know, times the weighting function is equals to 1. Okay, so that's how we're actually going to fix this R0. Okay, and the moment we do that, we also have that this delta function thing holds by definition. Okay, so that's what we mean by orthogonal basis function. So we can compute all these eigenfunctions. If you're working with P and Q are constant and W is a constant, then they're just sine and cosine functions. If they're not, you can always get them. And they always have the feature that they have these oscillating solutions with zeros. But exactly finding out where those zeros are and what the lambdas are is often numerics, but there are a number of actual equations to which we know the solutions. And we'll start looking at Matei's equation at the next one. Okay, so what we now want to do is we want to go back and say, let us consider any function f on the little interval that we're considering, so from a to b. So it's basically a map from of a to b to r. And the set of eigenfunctions yn with eigenvalues lambda n that solve your Sturm-Liouville problem and the boundary conditions. Okay, so we don't specify which Sturm-Liouville problem it solves. So there are several sets of these functions, one of which is sine and cos, but there are several others depending on the differential equation you're using. We just want one set. And then any function can be represented on the set. Okay, so then there exists Cn from 0 that are basically a set of numbers from 0 to infinity, so that you can express this function f of x as the sum of Cn multiplied by the basis functions. And the first step to show this is simply to give you a way of calculating Cn. And we've already had a taste of it when we calculated the Green's function. Okay. It's simply you take Cn, to get Cn, you basically take this definition of f and take its inner product with a different eigenfunction. Okay, so let's just to compute Cn, let's just see, let's first compute this inner product. So we basically take f of x, okay, we substitute in this expression that we've basically assumed it can be written as, and we take the inner product with ym of x, and then what we get is this thing, and this thing once again means we have to put it in this type of inner product. So it's basically an integral. And when we do that, we can exchange the order of integration with the summation. So we take the summation out, and we're left with this integral. But then we can apply the orthogonality relationship to those two functions, and we just get that that's equals to delta in m, and therefore the sum collapses to just Cm. Okay, so we basically have derived an expression for Cm. So Cm is just the inner product of the function you're trying to expand with one of the basis functions. So you're basically taking the projection of that function onto a particular basis function to work out this coefficient. Okay, so now the next result that's useful is that Cn is unique. In other words, suppose you have a function and you find one expansion for it. In other words, you get a series of number Cn, so that you write the function this way. If you were to get another series of numbers with the same set of Bayesian functions, then the numbers would be the same. And the way you prove that is simply subtract these two expressions of f. So you have 0 equals to Cn minus Dn times the basis functions. Okay, which is a bit messy. And the way you clean up the mess is simply you hit it with another of the basis functions, say with the mth basis function, and you take the inner product. Okay. But you know that the inner product, when you hit 0 with the mth basis function, just 0, and regardless of what you do to 0, it remains 0. Multiplicatively, of course. But the right-hand side, if you then formally work it out, is just the sum times Cn minus dnyn. Okay, and you can work out each of the integrals independently, so it just becomes, you exchange the order of integration summation, and you simply have that it's Cn minus dn delta nm, okay, and that's equals to 0. Okay, so you collapse, you're only left, because the delta function, you're only left with Cm minus dm. You know that's equals to 0, so Cm must be equals to dm for all m. Okay, which is enough to prove that your expansion is unique. The second thing is basically the one comment that I made earlier is that these coefficients are an equivalent representation of this function. All right, so you basically have a function that maps this interval, or you can represent it as the explicit definition of the function, or you can express it as these coefficients. The next thing is basically that different functions have different expansions, okay, which you also need, right? Otherwise, there'll be a lot of ambiguity. And the way we prove that is, suppose we have two functions with the expansions. So you have f is equals to Cn yn, and g is equals to gn yn. And let's suppose these expansions are the same for all n except for a particular one. Okay, so what we basically have is that if f is not equals to g, then it applies that even if the expansion is the same for all n except a particular one, then it must differ for that particular one. In other words, we're saying that there is at least one value n such that the expansion coefficients aren't equal. Okay. And to see that, consider basically f minus g, that's equals to the sum. Okay, and we assume that these things are equal for everywhere except for a particular n. Okay, so this thing cancels except for there. But now we know that y of n is not the trivial solution. That was an assumption we constructed. The eigen yn of x is not the trivial solution. That was an assumption when we actually constructed the eigenbasis. Okay, therefore, since we know that f minus g is not identically 0 and y is not identically 0, it can only be true if Cn is not identically equals to Gn. Okay, so different expansions for different functions differ in at least one coefficient. Okay, and that basically, I think, concludes what I'm going to do now. It just simply gave you the mechanics of how you expand a particular function on your basis equation or basis functions, these oscillating functions that are associated with a specific Sturm operator. And it makes it very, very useful actually when we start specifying our initial conditions or our boundary conditions to be able to actually do this. Okay, so that's going to be the application of this theory when we start looking at the PDEs, in particular the wave equation on the elliptical membrane, in the next lecture. Thank you very much. This